Hello students, welcome back. The final topic here is section 3, constraint optimization. A constraint optimization problem consists of two parts. A constraint condition, which is an equation of two variables, and the objective function, the function to be maximized or minimized. But there's a problem. We have two variables to work with. If you have just one variable, then great, we can take the derivative, set it equal to 0, and solve for that variable. We can do that. But if we have two variables, we have a problem. How do we work it out? The typical strategy is go to this constraint condition, solve for one variable, plug it into this objective function to reduce it into a function of one variable. Once we get that, then we can use typical calculus technique. Take the derivative, set it equal to 0, from that equation, find out that variable. It's not going to make much sense if I just work out just theoretically, so let's go over to an example problem here. An open-top box with a square bottom must have a volume of 32,000 cubic centimeters. Find the dimension of the box that minimizes the amount of materials used. This is a geometry problem, so pictures will help. Okay, we have an open-top box like this, which will be presented from here. I mean, if this had been a piece of paper, then you can cut through and then fold over, then you're going to get this box. Do you see it? Now, we have to have a square bottom, so this part here should be a square. Width times length, that should be x by x. And then we have 4 square panels. Did I say square panels? Sorry about that. We have 4 rectangular panels, the side panels, and those have different width and height. In summary, this is what we're going to get. So that's x, and that too is x, so that down here we have a square with the area of x squared, and then side panel is y. They're all y, so that, if you fold over, height is y. Make sense? Okay, now read the problem again. The volume of 32,000 cubic centimeters. So this number is given. Something is equal to 32,000, and that's volume. So volume, and look at this right-hand side 3D figure, and that is base area times height, and that is 32,000. All right, this gives us the constraint condition. Now, what is the objective function, the function to be optimized? Well, let's go to this 2D figure, and then the area here, down here, the bottom square is x squared, and then 4 side panels. So the area here is x squared plus 4xy. Why 4? Because there are 4 side panels. Each of them has area x times y. Now, if you take the derivative, set it equal to 0, and solve for a variable, yeah, you can do that, but there's a problem. We have 2 variables here. So what we are going to do here is to solve for y. So 32,000 over x squared from this constraint condition. And then if I plug it right here, then I'm going to get a function of one variable only. Just function of x. All right, take the derivative, set it equal to 0, find out that x value, and that's how you can do this optimization. So constraint condition, which we got from geometry, and then objective function, again, we got it from the geometry. So for one variable and plug it into the other, then I have a function of one variable to work with, so that I can take the derivative and set it equal to 0. That is the strategy. Okay, let's begin. Let's get out of drawing mode now. Okay, here we go. Constraint condition, which comes from volume. Objective function, which comes from the surface area. Not exactly surface area. Oh yeah, it is surface area, excuse me. we have open top. There's no top, so. All right. So for one variable, y equal to 32,000 divided by x squared. Now plug it into this y right here, so right there. And then if you simplify, you're going to get the final expression there. X squared, that comes from, the square, bottom square, and 4x times this quantity, and x to the first power times x to the second power in the denominator. So we have just x in denominator. But for calculus, power form is usually more convenient, so I used x to the negative first power form instead of 128,000 over x. You could have write it as 128,000 over x if you prefer. You can do it like that too. Now take the derivative. X squared became 2x, and this became, let's see, negative 128,000 x to the negative second power. That's the derivative computation. Multiply by the power and subtract 1 from the power. So this is equal to 0, so solve it. Flip this one to the other side. 2x is equal to 128,000 over x squared. I could have used negative second power too if I wanted. Anyway, let's solve it. Flip this to the other side, I get x cubed, and divide by 2, and I get 64,000. And then pick up your calculator and calculate your cubing root. Cubing root of 64,000. As a matter of fact, this is so simple that you can do it even with your mental math. It's 40. And then, looking for y, well, it's right here. So when x is 40, then plug it in, do your computation, and you're going to get 20. So we have the dimension. X is 40, y is 20, which means 40 here, 40 there, and then 20 there. So this open top box is 40 by 40 by 20. Oh, by the way, one more thing. The moment you have the objective function straightened out, probably it's a good idea to plot it. Let's copy and paste this thing. And then, yeah, as you can see, we have absolute minimum taking place at x equals 40. And then if you do your computation, yes, indeed, at x equals 40. Okay. Now, let's go to the next problem. How about this? An open-top box with a square bottom must have the volume of 32,000 cubic centimeters as before. Suppose further that the material for the bottom is twice as expensive as the material for the side. Again, the same situation. And then same labeling. We have x by y. And then the volume is going to be, well, that's the same. So the objective function becoming v equals to x squared times y equals to 32,000. Therefore, y equals 32,000 over x squared. That much is going to be identical. Now the question is, what is the objective function? Cost of this material. Well, the bigger the area, the more expensive it will be. And then, well, if it is $1 per square centimeters, then 1 times the surface area. $2 per square centimeters, then $2 per times surface area, things like that. But there's a bit of a problem here. This bottom is twice as expensive. So somehow you have to adjust for that. How do you do that? Try to figure it out on your own. Stop the playback and try to figure it out on your own. What do you have? Did you get it? Well, here we go. Here's the solution. you have to multiply by 2. 4 side panels here, that's the same, but the square part, the bottom part, is twice as expensive as the other part, so multiply by 2. Excuse me. If the bottom part had been, say, 5 times as expensive, then you have to multiply by 5. Make sense? In any case, in this case, we have to multiply by 2 so that you get the objective function. As for the constraint condition, it's the same because it's coming from the volume. And so for y, then we get this, and plug it in right here, then you get the objective function straightened out. A bit of a simplification later, you get this. The primary difference between, actually not primary difference, the only difference between the previous problem and this problem is this factor of 2. That's the only difference. Otherwise, the same. Now, taking the derivative and setting it equal to 0, yes, you can do that. Let me scroll down and show you a little bit. Take the derivative, set it equal to 0. No problem, you should be able to do that. And solving for this, yeah, that's easy too. Flip this over to the other side, and then do your computation. Flip this x squared to the other side, so x cubed. And then dividing by 4 from both sides, we have x cubed is 32,000. Pick up your calculator and calculate your cubic root. I got about 31.75, and of course, it's going to be longer if you take all those digit strings, but let's stop here. And then plug it in. You're going to be able to find that y value, and by some strange coincidence, I ended up with the same value. Actually, it'll turn out it's not a coincidence, as a matter of fact. What do you mean by twice as expensive? Well, you ended up with 2x squared, so this thing is equivalent to having the top as well. You see, this bottom part is twice as expensive and no top. So equivalently speaking, same materials, same cost, and top as well. That is actually the equivalent situation here. So when this volume is fixed, biggest surface area is coming from the symmetric situation when we have a cube. So x and y are the same. So 31.75 by 31.75 by 31.75. When we have a cubic configuration, that's the optimal case in this particular case. Oh, by the way, as long as you have this objective function, you can always plot it. Let's see what we have. We have absolute minimum forming somewhere around here, around 30. And if you do your computation, it's pretty close to 30, 31.75 approximately speaking. So yes, it fits pretty well. Okay, we went through a couple of problems, and as a matter of fact, both problems revolved around the same geometrical configuration. So getting the constraint condition especially was the same. Now let's consider a significantly different problem. But then again, in constraint optimization, I can go overboard very quickly because things can get really complicated really quickly. And the next example is kind of like that. Let me just show you the visualization and then just stop here because this is way too complicated for 1325 level. So we have an ellipse like this, and we have x comma y, and we want to find out the biggest rectangle that we can fit in. What's the area of this rectangle when I have this x comma y there? Well, that's it actually. That is the objective function. Oh, by the way, constraint condition is explicitly given here. 2x is the width here because from here to there is x, so 2x, and then times 2y. That's how we get the area. And if you work it out, you're going to get something, but it's too complicated. I'll stop here.